phase starts by increasing the vertical stress applied to the specimen. The minor principal stress sigma 3 does not change as we shear the specimen. We continue to increase the vertical stress until the specimen fails. Again, the maximum principal stress at failure is sigma 1F, and the soil has an undrained strength SU. Because the drainage valve was closed during the consolidation phase, no consolidation occurred, and the soil did not gain any strength during this phase. Therefore, the undrained strength under confining stress is no greater than the undrained strength measured by an unconfined compression test of the same soil as shown here. Similarly, if we conduct another test on an identical specimen, but raise sigma 3 during the consolidation to the point shown, the soil still would not gain any strength because no consolidation is allowed. This third test would also have the same undrained strength as the two previous tests. If we plot the total stress failure envelope for the test, it will have zero slope and intersect the tau axis at SU. This is known as the phi equals 0 condition. Saturated clays loaded in undrained conditions fail under phi equals 0 conditions. Now let's consider the consolidated drained or CD test. In this test, the drainage valve remains open during both the consolidation and shear phases, and any excess pore pressures that might be generated are allowed to dissipate, so there's no excess pore pressure. Therefore, the effective stress and the total stress are equal. This is an effective stress test. During consolidation, the Mohr circle again moves from a point at the origin to a point at the consolidation stress sigma 3. But in this case, sigma 3 is an effective consolidation stress because there are no pore pressures and the soil will consolidate and increase in strength. Sigma 1 is then increased until the soil fails. But in this test, the shearing is done so slowly that no pore pressures are generated. Therefore, the major principal stress at failure is also an effective stress. If we test a second specimen, but consolidate it to a higher confining stress, the soil will gain strength during the consolidation process. When it is sheared, it will have a larger Mohr circle at failure as shown. Likewise, if we run a third test at yet a higher confining stress, again the soil will consolidate and have an even larger Mohr circle at failure. Using the three failure circles shown, we can plot the failure envelope as the line tangent to the circles and compute the friction angle phi prime and cohesion C prime. In this case, this will be an effective stress failure envelope, and phi and C will be effective stress parameters as noted by the use of the prime symbol. Let's look at our final test, the CU test, or consolidated undrained test. In this test, the drainage valve is open while the confining stress is applied and remains open until the soil is consolidated and all pore pressures are dissipated. The drainage valve is then closed, creating an undrained condition for the shear phase of the test, and we will be measuring any excess pore pressures that are generated during shear. The vertical stress is then increased until the soil fails. Since we are measuring pore pressures during the test, we know the change in pore pressure at failure, delta U. Knowing both the total stresses and the pore pressure at failure, we can compute the effective stresses at failure and plot the effective stress Mohr circle shown here with dashed lines. This circle is offset from the total stress circle by a value of delta U. In this case, we have a negative excess pore pressure, so the effective stress is greater than the total stress, shifting the Mohr circle to the right. As in previous tests, we can test a second specimen at a higher consolidation stress. We can then shear this specimen until it fails and determine the total stress circle at failure for the specimen. Again, we'll know the pore pressures at failure, so we can also plot the effective stress circle at failure, here shown with dashed lines. Finally, we can test a third specimen at a higher confining stress, and we will obtain another set of total and effective stress circles at failure. We now have two sets of failure circles. The solid circles represent total stresses at failure, and the dashed circles represent the effective stresses at failure. If we consider just the effective stress circles, we can plot the effective stress failure envelope and determine the strength parameters phi' and C'. Therefore, from a CU test with pore pressure measurements, we can determine the effective stress strength parameters even though the shear phase is in an undrained condition. So now that we've covered the basic triaxial tests, let's discuss some of the advantages this test has over the direct shear test. The triaxial testing procedure gives us control over drainage conditions both during consolidation and shear. Therefore, it allows us to measure either the drain strength or the undrained strength of a soil. The shear plane is not confined to a fixed plane as it is in the direct shear test. This gives us a more realistic failure surface and a better measure of the strength of a soil. The boundary conditions are controlled and known. This allows us to plot complete Mohr circles and determine the stresses on the failure plane. Finally, we can measure both axial and volumetric strains during the test, which allows us to measure the stress-strain properties of the soil. So let's summarize. The triaxial test has the following characteristics. The test is relatively difficult and time-consuming to run, with the exception of the UU test, which can be run very quickly. However, both the CD and CU tests must be run very slowly so that shear-induced pore pressures can dissipate or equilibrate throughout the specimen. The data is more difficult to analyze than the direct shear data, but at the same time we get much better information from these tests. Finally, the strength parameters measured in the triaxial test are more accurate than those measured in the direct shear test. You should now review the learning objectives for this presentation. If you don't feel you've achieved these objectives, now would be a good time to review the presentation. Example 12.10 in your text